In the last video we talked about limits, and we talked about that a limit is a y value that's being approached as we approach a particular x value. In this video we're going to, we also talked about in the last video the strategies or the techniques to find a limit. One of them was graphically. A second was to use a table. And the third was analytical, using algebraic approaches. So we're going to examine some analytical approaches to finding limits. So we are to determine the limit of a function, or it says to determine the limit of a function, always try direct substitution first. This technique will always work on a continuous function. So let's think about that. A continuous function, as you recall from a prior course, is a function that basically has no breaks or no gaps or no holes in it. So things like lines, that's a continuous function. And on that line, if we approach any given x value, it doesn't matter the x value. So let's say that I'm approaching, well, let's call this 1 and this 2. Let's say I'm approaching 2. Well, if I approach from the left-hand side and from the right-hand side, the y value that we are approaching will actually be the y value of the function. I don't have any breaks or gaps or holes to worry about. Likewise, if I were to think about a parabola and I'm approaching an x value of 2, since this function is continuous, again meaning it has no breaks, no gaps, no holes, in other words no vertical asymptotes, no horizontal, nothing like that, the left limit and the right limit would always have to agree with each other. So if we know that we're dealing with a continuous function, then to find the limit, it's just going to be the y value. So we'll use direct substitution to find those limits. Alright, let's take a look at some of these examples here. In number 1, we're finding the limit as x approaches 3 of 7. Now, the function in this case is 7, so this is really implied that f of x is equal to 7, which is the same thing as y equal to 7, which is a horizontal line. So, the y value on a horizontal line is always 7. So, regardless of what we approach, even though in this case we're approaching 3, the y value, or the limit that we would be approaching, is the number 7. Alright, let's take a look at number 2. That was pretty easy. In number 2, we have a quadratic function, which is a second degree equation, and if we were to graph it, we would get a parabola. And we know from our prior experience that a quadratic function, or parabola in this case, is a continuous function. So we don't have to worry about the left and right limits disagreeing with one another. So if I want to find the limit, I'm actually going to use direct substitution. So I would have 2 squared plus 2 times 2 minus 1. So 2 squared is 4 plus 4 minus 1. So the y value that we are approaching on this particular function, if we had a graph, we'd be approaching a y value of 7 as we get closer to an x value of 2. Both of those functions are continuous. Life is good when we have continuous functions. In number 3, we have another quadratic function which would graph to be a parabola. It is continuous. Continuous is good because if we have a continuous function, then we can use direct substitution. We're approaching an x value of 3. 3 squared is 9, minus 9 is 0. So if we had a graph, we'd be approaching a y value of 0. Number 4, cosine. Well, we know that cosine has a period of 2 pi and looks something like that. We know that cosine is a continuous function, has no breaks, gaps, or holes. So, since it's a continuous function, as we approach an x value of 5 pi over 6, the y value would be what we get when we substitute 5 pi over 6, cosine of 5 pi over 6. Remember that 5 pi over 6 is in the third quadrant. It's over here. Whoops, sorry. In the second quadrant. And in the second quadrant, the cosines are negative. So we're going to get a negative output. Since it's 5 pi over 6, that refers back to a 30-degree angle, and the cosine of 30 degrees is root 3 over 2. And you do need to know those values. All right, number 5. Now in number 5, this is just a stray mark that got into the flip chart. So in number 5, we're finding the limit as x approaches 0 of e to the x. We know that e to the x is an exponential function that looks something like that. The important part is that it is a continuous function, has no breaks, gaps, or holes. So we can use the strategy of direct substitution. E to the 0 is 1. So as we move towards an x value of 0 on that function, we are approaching a y value of 1. Good stuff, as long as the function is continuous. All right. What if the function is not continuous? Again, if the function is not continuous, then there may be a break, there may be a gap, there may be a hole, and in those cases we have to examine very carefully what's happening from the left and what's happening from the right to see if they agree. So analytically, how do we deal with that? Well, first of all, if you take a look at number 2, the limit as x approaches negative 5. If we try direct substitution, which is what I should always do first, if we substitute negative 5 in place of x here, we'll get 0 in the denominator, and we know that division by 0 is undefined, so that's not going to help us out. But I notice that the numerator is a quadratic, and I can factor it. So I'm going to try to do a rewrite. This is what I was talking about using algebraic techniques. So that would be the limit as x approaches negative 5, factoring the numerator, 5 and 2 and plus and minus, and notice what happens. We have what is called a removable discontinuity because I literally can remove it by factoring and reducing. Now that I've removed the discontinuity, limit as x approaches negative 5 of x minus 2, no longer now do I have that factor of x minus 5, x plus 5 in the denominator, so I now can use my direct substitution, and I'll get a y value of negative 7. Now graphically, what's happening here, you may or may not remember this from pre-cal, after I created that removable discontinuity, what I had left over basically was the function y equal to x minus 2. So from pre-cal, you'll remember that at negative 5, 1, 2, 3, 4, 5, I would have an open circle, 3, 4, 5, 6, 7, here. And then the line, let's see, my slope is rise 1 run, so my line would look something like that. It's a graph with a hole in it. The limit does exist because as we approach from the left side and from the right side, we are moving closer to the same y value. Even though we can't get there, what we are approaching agrees. Next example. Another strategy is to rationalize the numerator. Now the reason I'm thinking rationalize is because I see radicals, and you may or may not remember from geometry. In geometry, interestingly enough, you were always told to rationalize the denominator, get the radicals out of the denominator. Well, now all of a sudden you're being told to put the radical back into the denominator, and I think if you follow, you'll see why we're doing that. So again, the first thing I'm going to try to do is direct substitution, but I got a problem. If I let x be 0, I have 0 in the denominator, and division by 0 is undefined. So I'm going to multiply by 1, and I'm going to represent that 1 as the conjugate of the numerator. Now you will hopefully remember from a preceding course that when you multiply by the conjugate, multiply a radical expression by the conjugate, it basically simply just gets rid of the radicals for you. So if we multiply that out the long way and we multiply these two terms together, that'll lift the radical, and I get, whoops, don't let me get away with that. I have to write limit. So this is still the limit because we have not found the limit yet as x approaches 0. All right, now multiply them together. and I get x plus 1. Multiply square root of x plus 1 by 1, and I get positive square root of x plus 1. Multiply negative 1 by square root of x plus 1. So those two terms, those two middle terms, are going to cancel out because one of them is positive and the other one is negative, which is exactly what I wanted to happen. I wanted the radical to go away. And then negative 1 times 1 is negative 1. Now in the denominator, notice that I'm not going to distribute the x. I'm going to leave it as an implied multiplication problem. And you'll see why in just a second, or you probably already see why. In the numerator, the 1's are going to subtract out, and so I'm left with the limit as x approaches 0 of x over x times the square root of x plus 1 plus 1. I think you can see what's happening. The x's are going to divide out, leaving me in the numerator with a 1. So now I can use direct substitution, and I'll get 1 over the square root of 0 plus 1 plus 1, which is going to be 1 over 1 plus 1, which is 1/2. Now you may have to watch that again to pick up that strategy. It's not that difficult, but it's rationalizing the numerator. If we were to take a look at that graph, we would notice that as we move towards an x value of 0, we are approaching a y value of 1/2. And you see in number 8, another radical. But before you do that, you got to be careful, because it may not be that we're approaching the discontinuity. There's only an issue if we're approaching where the discontinuity occurs on the function. So before you jump in and start doing all that rationalizing the numerator, try direct substitution. Of course, I set this up so that that would approach the discontinuity, and we have another chance of practicing rationalize the numerator. So I'm going to multiply by 1. In other words, the conjugate over itself, so x plus 1 plus 2. Remember the conjugate, you change that sign. That will give me the limit as x approaches 3. Multiplying that out will give me x plus 1. The radicals will subtract, minus 4. Don't distribute that denominator through, because we want that factor in the denominator to divide out. That gives me the limit as x approaches 3 of x minus 3 over, see, there it is. That's going to remove my discontinuity. I'm manipulating this algebraically. The x minus 3's divide out, and I can substitute the 3 in, which would give me 1 over square root of 3 plus 1 plus 2. 3 plus 1 is 4. Square root of 4 is 2, plus 2 is 4. So the y value on that graph that we are approaching as we approach an x value of 3 is 1/4. And these are strategies that you're just going to have to be aware of and practice, and you have to examine each problem and basically learn how to use the right tool for the right job. You can ignore this homework. This is an old flip chart. In fact, let's just get that out of the way. Get that out of the way. Get that out of the way. All right, so trig functions. When you encounter a trig function, it doesn't have a radical in it. It's not factorable, or at least this one's not. So what do you always try first? Let's back up. There is a discontinuity on this graph. Anywhere that the sign is equal to 0, we have a discontinuity. So we have to be careful. But first thing you always try to do is try direct substitution. So tangent of 0 over sine of 0. Well, if you think about the unit circle, the y value at 0, which is right here, is 0, so can't use direct substitution. So I have to use think about my trig substitutions. I know that tangent can be rewritten as sine of x over cosine of x. This is my replacement for tangent. Now I have a fraction divided by a fraction, so basically I have sine x over cosine x divided by sine x over 1, because there's my over 1, which is the same thing as sine x divided by cosine x multiplied by the reciprocal, 1 over sine x, and look what happens. The sine x's divide out, and that's equal to the limit as x approaches 0 of 1 over cosine of x. So I have removed my discontinuity. I can substitute 0 in. So this is 1 over cosine of 0. The cosine of 0 is 1, so I get 1 over 1, which is 1. So as on that graph, as I approach an x value of 0, I'm approaching a y value of 1.